All right, so in this video, we're going to look at how we can visualize sequences graphically, and then we're going to discuss some terminology associated to sequences and look at some examples. All right, so first off, I just want to highlight the fact that a sequence a sub n defines a function f whose domain is the set of positive integers. Okay, so the way this works is that if I have a sequence a sub n, well then I can consider this function f whose input n just takes on positive integers, right? 1, 2, 3, 4, so on and so forth. And the outputs are just the associated a sub n's, right? They're the terms of the sequence. So as an example of this, if I have the sequence whose nth term is n over n plus 1, right, this defines the function f, where I have that f of n is just, well, n over n plus 1, right? So, for example, f of 3 would just be 3/4, just plugging in 3 for n, and that's just telling me that the third term of this sequence is 3/4, right? So the input is really just the index, and the output is just the associated term of the sequence, okay? So these input-output pairs then can be plotted on a graph, and this gives us a nice way to graph the sequence. So to illustrate that, let's look at the graph of the sequence n over n plus 1, right? So for example, a sub 1 is 1/2. So I'm going to plot the point 1 comma 1/2 to just express the fact that, well, the first term of the sequence is 1/2. Then I have that a sub 2 is 2/3, so 2 comma 2/3. Then a sub 3 is 3/4, so that'd be 3 comma 3/4, so on and so forth, right? So this gives us a very nice visual representation of the sequence. And from this graph, right, a few things immediately stand out. So the first thing to note here is that as n increases, the terms approach 1, right? And I can just see that graphically. You see this dashed red line here. This is at 1. This is just a horizontal asymptote for the sequence, and that's being expressed here in limit notation, just saying, well, as we let n approach infinity, all right, our terms approach 1. Now we'll go ahead and get into limits in a whole bunch of detail in a little bit, but for now we'll just mention this in passing. All right, so another thing that's pretty apparent here is that the terms are increasing, right? You see this increasing behavior, and I can write that notationally as a sub n plus 1 is greater than a sub n, and that's true for all n. And that's really just saying, well, if I look at any term, say a sub 3, okay, well, it's larger than its predecessor, right? So a sub 3 is larger than a sub 2, a sub 4 is larger than a sub 3, a sub 5 is larger than a sub 4, so on and so forth, okay? So it's an increasing sequence. And then the other thing to note here is that this is what we call a bounded sequence, okay? So the idea with a bounded sequence, which I'll define in more detail here in a moment, is that we can, in essence, trap all of the terms in some finite band. Okay, so in this case, all of the terms of the sequence fall between these numbers 1/2 and 1. Okay, so for that reason, we call this a bounded sequence. All right, so now let's go ahead and define a few things. So, okay, the first definition we're going to look at is that of a monotonic sequence. And so essentially, a monotonic sequence is a sequence whose terms move in one direction, so to speak. Okay, so we'd say that a sequence a sub n is monotonic increasing if a sub n plus 1 is greater than or equal to a sub n for all n. Okay, so at any term, like let's say a sub 3, okay, well, it's going to be less than or equal to its successor. Okay, so what that says graphically is that I'm either going to move up or I could potentially flatline because of the inequality being a greater than or equal to. So I'm either going to be increasing or flatlining. But if I'm monotonic increasing, then what I cannot do is turn around and go down. Okay, so I am going to be moving in one direction, in this case, the increasing direction. Likewise, I say that a sequence is monotonic decreasing if a sub n plus 1 is less than or equal to a sub n. So that's going to say that the terms can go down, or again, I could potentially flatline. But what I cannot do is start to increase. Okay, so monotonic increasing up here, decreasing here. this example shows a sequence that's neither monotonically increasing or decreasing. So we just say there that the sequence is not a monotonic sequence. And the reason why is that, well, I decrease here to here, and then I increase. And so these first three terms are enough to say that this is not a monotonic sequence because, again, I'm not, in this case, moving in one direction. All right, cool. So next up, let's go ahead and define what we mean by a bounded sequence. And so again, the intuitive sense of being bounded just means that all the terms of the sequence fall within some band. Okay, so to be a little bit more precise there, we say that the sequence a sub n is bounded if there exists some positive number m such that the absolute value of a sub n is less than or equal to m, and that's true for all n. Okay, so in other words, I can find some bound where all the terms fall in this band between minus m and m. Okay, so here's two examples to illustrate. So for the first sequence here, I have the a sub n is just n. Okay, so 1, 2, 3, 4, so on and so forth. Okay, this is not a bounded sequence. Okay, by making n sufficiently large, I can make the a sub n's sufficiently large. So there's no m that will contain all of the terms, in other words. Okay, so like if you say, well, what if m was 1,000? Well, I'm eventually going to escape the band from minus 1,000 to positive 1,000 once I get to the 1,001st term, right? I'm going to break out of that band. Okay, contrast that with this second sequence where a sub n is negative 1 to the n minus first power divided by 2 to the n. Okay, so here I have 1/2, comma negative 1/4, comma 1/8, negative 1/16, so on and so forth. So here, right, I'm going down, then up, then down, then up. And notice, right, the magnitude, or in other words, the absolute value of the terms is steadily decreasing because of the 2 to the n term in the denominator. Well, all of these terms you see here, right, are within this band between negative 1/2 and 1/2, right? They're all contained or trapped in this band. So this is a bounded sequence. All right, cool. So now to finish here, let's look at those examples from the first video. Okay, the first sequence there was just the positive odd integers, 1, 3, 5, 7, so on and so forth, and here's its graph. The second sequence was n over n plus 1, which we've already looked at in this video. So 1/2, 2/3, 3/4. Okay, there's its graph. And then the last sequence there was a sub n, which is n times the cosine of pi n, and that was negative 1, 2, negative 3, 4, so on and so forth. So there's that graph. So take a few moments, maybe pause the video, ask yourself, is the sequence monotonic and is it bounded? Okay, and here are the answers. So the first sequence is monotonic increasing, right? The terms are steadily increasing from one to the next, and this thing is not bounded. I cannot contain all of the terms within some finite band. The second sequence, this is also monotonic increasing, as we noted before, and this is also bounded. Now, earlier I said, right, all the terms are trapped between 1/2 and 1. Now, using uh, the definition that I gave for bounded sequences with the absolute value, I could just set my m value to 1, right? Because all the terms are certainly between negative 1 and 1, right? So they're all within a finite band. Now the third sequence here, this is not monotonic, right? I increase, but then I decrease, and then I increase, and then I decrease. It really, again, these first three terms are enough to determine that this thing is not monotonic. And it's not bounded either, right? Because as I let n increase, the absolute value of the terms becomes infinitely large. Okay, so I cannot contain all of the terms within some finite band. Okay, now in the next video, we're just going to look at a whole bunch of additional examples, and this is problem 1 on the 9.1 and 9.2 worksheet. So I encourage you to do as many of these as you can before watching that video. You'll notice also in part D, there's this what's called a factorial, n with this exclamation point. I'll say some things about factorials. This may or may not be familiar to you, but again, check that out and then watch the video for solutions. All right, see you there.